Hi friends, in this video we are going to discuss theories of failure under static loading conditions. So first we want to know how the material fails. There are two kinds of materials, brittle material and ductile material. Brittle material are very good in shear so that it will fail in normal stress, whereas ductile materials are very good in normal stress, so it will be failing in shear stress. So experiment suggests that for no failure of material, tau max must be less than or equal to 0.577 times of sigma y. Tau max is maximum shear stress, sigma y is normal yield stress. So we are going to discuss 5 theories of failures which are proposed by different scientists. First theory is maximum normal or principal stress theory. Second theory is maximum normal or principal strain theory. Third one is maximum shear stress theory. Fourth one is maximum shear strain and fourth one is maximum strain energy theory, and fifth one is maximum shear strain energy theory or maximum distortion energy theory. So these theories are also known as Rankine theory, Saint-Venance theory, Guest and Tresca theory, Heinz and Beltramis theory, and Henke-von Mises theory. So each different theory proposes different values. So according to Rankine theory, tau max is equal to sigma y. According to Saint-Venance theory, it is 0.77 times of sigma y. According to Guest and Tresca theory, its tau max is equal to 0.5 sigma y, and according to Higgs and Beltramis theory, tau max is equal to 0.62 times of sigma y, and according to Henke von Mises theory, tau max is equal to 0.5 times of sigma y. According to Henke and von Mises theory, tau max is equal to 0.57 times of sigma y. See, these values are proposed by different scientists according to their own derivations. See, Rankine theory, Rankine considered only maximum normal stress. That is, he not considered the shear stress. So normally brittle material are very good in shear. So we don't want to check for shear stress. So instead, here we will be checking only the normal stress. If the material is good in normal stress, that is, if the brittle material is good in normal stress, definitely it is going to withstand shear stress. So this theory is normally we are applying for brittle material. So in case of Saint Venance theory, same thing. In this theory, he is going to consider the maximum normal strain, so that if the brittle material is good in normal, definitely it is going to good in shear. So this theory we are particularly using for brittle materials. Third theory is Guest and Tresca's theory. In this theory, we are going to consider the maximum shear stress. So normally ductile material is good in normal stress. So if we check for shear stress and if the material is safe, definitely it is going to be safe in normal stress also. So here we are considering only the shear stress. So this is applicable for ductile materials. So same case for maximum strain energy theory and maximum shear strain energy theory. So each different theory have a different failure envelope curve that we will be discussing later. So after doing series, after doing series number of experiments, we came to know that tau max must be less than or equal to 0.577 times of sigma y. But if we check here, the but if we check in Saint Venance theory, it's tau max is equal to 0.77 times of sigma y, so which crosses 0.577. So normally we are not going to use this theory. And in fourth theory, Higgs and Beltramis theory, it's 0.2 sigma y. Again, it crossed the 0.577. So we are not going to use this theory also. Here, this is normal stress. So we are not going to consider the shear part. So tau max we can take it as sigma y directly because in normal. So now we will be discussing the each different theories of failures in detail. So first is maximum principal stress theory. What is principal stress? Principal stress is sigma. So sigma 1 is maximum principal stress. And sigma 2 is minimum principal stress. So according to our theory, the stress what we are applying, that is or actual, that must be less than or equal to sigma yield. So this sigma yield is a constant for different materials. So what, this is the actual stress we are applying. So this actual stress must be less than or equal to sigma yield. So this sigma 1, sigma 2 must be less than or equal to sigma yield. How to calculate sigma 1 and sigma 2 is, we know that we have a formula that sigma x plus sigma y by 2 plus minus root of sigma x minus sigma y by 2 the whole square plus tau xy square. So if the calculated sigma 1, sigma 2 value is less than or equal to sigma yield, then we can consider the material is safe. By using this, by using this equation, we can make this graph. This x-axis represents plus sigma 1, this represents minus sigma 1, this represents sigma 2, this represents minus sigma 2. From this equation, we can able to make this graph. Next, we are going to discuss maximum principal strain theory. Principal strain is epsilon 1 and epsilon 2. So as I told earlier, epsilon actual must be less than or equal to epsilon yield. So epsilon actual is epsilon 1 comma epsilon 2 less than or equal to sigma yield by E. We know Young's modulus is equal to stress by strain. From this, I have taken this. So epsilon 1 can be written as epsilon 1 can be written as sigma 1 by E minus mu into sigma 2 by E. Epsilon 2 can be written as sigma 2 by E minus mu into sigma 1 by E. So if these two values are lesser than sigma yield by E, so now we are going to apply these two equations here. So we will be getting sigma 1 by E minus mu into sigma 2 by E, which must be less than or equal to sigma yield by E. So after cancelling E, we will be getting sigma 1 minus mu times sigma 2 less than or equal to sigma yield. If I put other equation, I will be getting sigma 2 minus mu times sigma 1 less than or equal to sigma yield. So again, we want to use these equations to so with the help of these two equations, I'm going to draw this graph. So this is plus sigma 1, this is minus sigma 1, this is plus sigma 2, this is minus sigma 2. From this equation, I can able to draw this graph. This is not important. So next we are going to discuss maximum shear stress theory. That is the tau actual what we are going to apply, that must be less than or equal to tau maximum. So tau, we are getting the formula as sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 1 minus sigma 3 by 2, which must be less than or equal to sigma yield by 2. So sigma 1 minus sigma 2 slash comma sigma 2 minus sigma 3 comma sigma 1 minus sigma 3 must be less than or equal to sigma yield. So for 2D cases, we want for 2D cases, we will be putting sigma 3 as 0. So we will be getting sigma 1 minus sigma 2 comma sigma 2 comma sigma 1, which should be less than or equal to sigma yield. From here we'll be getting this graph. Here we're going to discuss maximum strain energy theory. That is, strain energy actual what we are going to give to the material, that must be less than or equal to strain energy maximum that can be stored. So strain energy formula is 1 by 2E sigma 1 square sigma 2 square sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3, which must be less than or equal to sigma square yield by 2E. See, strain energy is sigma square by 2E, which we must be remembering this formula. So for 2D cases, if I write for 2D cases, for 2D sigma 3 is 0, so we'll be getting 1 by 2E sigma 1 square sigma 2 square minus 2 mu sigma 1 sigma 2, which must be less than or equal to sigma e square yield by 2E. After cancelling sigma e sigma e 2E 2E, I'll be getting sigma 1 square sigma 2 square minus 2 mu sigma 1 sigma 2, which must be less than or equal to sigma square yield. So from this is an ellipse equation, so I'll be getting the kind of ellipse. This is sigma 1 sigma 2 minus sigma 1 and minus sigma 2. Here we are going to discuss maximum strain energy theory, or we can call as maximum distortion energy theory. Here same thing, U is a strain energy. We'll be using designating strain energy as U. So U actual, that is, must be less than or equal to U maximum. U actual is 1 plus mu by 3E sigma 1 square sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 sigma 2 sigma 3 sigma 1 sigma 3, which must be less than or equal to 1 plus mu into sigma square by 3. For 2D case, 1 plus mu by 3 sigma 1 square sigma 2 square minus sigma 1 sigma 2, which must be less than or equal to sigma square 1 plus mu by 3e. So after cancelling this, I'll be getting sigma 1 square sigma 2 square minus sigma 1 sigma 2, which must be less than or equal to sigma square. So from this, I'll be drawing this graph. Plus sigma 1 sigma 2 minus sigma 1 plus sigma 2. Now if we consider maximum shear stress theory and maximum distortion energy theory, actually we can apply up to 0.57577 times of sigma y, but in this theory it is showing as 0.5 sigma y, which means we are in the safer zone. So this is safe but uneconomical, that is, we are unnecessarily wasting the material. Here exactly what the experimental value shows, we are getting the same value here. So 0.57 times of sigma y, this is 0.577 sigma y, which means here we are safe, both economical. Economical means we are not wasting any material. Here we are extra safe, here we are extra safe, and here we are accurate. So with this, I'm going to end this video. Thank you.